and welcome. If you are new to this channel, hi, I'm Anchita Divakran. Welcome to CodeGenix. In this channel, we discuss about all the things related to technology and programming. This video is a part of a series called Data Structure and Algorithm using Python. In previous video of this series, we discussed about what data structure is, types of data structure, then what an algorithm is, and properties of algorithm. If you haven't watched it yet, I will leave the link somewhere in the video and also in the description box below. Today, we will discuss about an important concept in algorithm called algorithm analysis. The topics are shown in the screen. I have written down the timestamps in the description box below. Feel free to skip to the topic that you want to know. So without wasting any time, let us dive right into this video. First, we will go through a small recap of what algorithm is and its properties. An algorithm is any well-computational procedure that takes one or two values as input and produces some values as output. Some properties of an algorithm are: an algorithm must have values from a specified set. An algorithm must produce output values from the specified set of input values. For any input, an algorithm must terminate after a finite number of steps. Each instructions or steps in an algorithm must be clear. Last but not least, the algorithm should be efficient. Notice the last property of the algorithm? See, it is about getting an efficient algorithm. So, how is it made possible? Is there any way to get this done? Well, yes. This is where the need of algorithm analysis comes. Algorithm analysis. Algorithm analysis is an important part of computational complexity theory, which provides theoretical estimation for the required resources of an algorithm to solve a specific computational problem. Most algorithms are designed to work with inputs of variable length. To put it in simple words, the analysis of algorithm is to mainly find the amount of time and space resources required to execute it. But why do we need algorithm analysis? Even though some of the algorithms have same objective, they are mostly different from one another. Hence, the time complexity of those algorithms may differ. At the same time, we need to calculate the memory space required by each algorithm. To solve a problem, we need to consider time as well as space complexity, as the program may run on the system where memory is limited but adequate space is available, or maybe vice versa. For example, to sort a set of numbers, we can use different types of algorithm. Let's compare two types of sorting algorithm: bubble sort and merge sort. In case of space complexity, the bubble sort is better to use as it do not consume extra space like merge sort. In case of space complexity, the bubble sort is better to use as it do not consume extra space like merge sort. In case of time complexity, bubble sort is better if there is few elements than merge sort. Generally, we perform following types of analysis: worst case, best case, and average case. Worst case, the maximum number of steps taken on any instance of size A. Best case is the minimum number of steps taken on any instance of size A. And average case is an average number of steps taken on any instance of size B. As we said before, the complexity of program is determined by the time or space complexity. So let us see more about the time and space complexity. Space complexity. It is the amount of memory space required by an algorithm in its life cycle. The space required by an algorithm is equal to the sum of the following: fixed part and variable part. Fixed part is a space required to store variables that are independent of the program size, like constants. And variable part is a space required to store variables that are dependent on the program size. Let us understand space complexity with an example. Given our problem statement, to find the sum of two numbers and add a constant 10 to it. The algorithm for the problem definition is as follows. Here, we have three variables A, B, and C and a constant 10. So, the total space complexity of our problem will be 1 plus 3, that is equal to 4. Moving on to our next type of complexity, time complexity. Time complexity of an algorithm represents the amount of time required by an algorithm to run to completion. Let us understand time complexity with an example. Given our problem statement is to print hello world. The algorithm for the problem statement is as follows. In the above algorithm, hello world prints only once. So the time complexity is constant, that is big O of 1. That is, every time the constant amount of time is required to execute the code, no matter which operating system or which machine configurations you are using. You can see that in the example that we have discussed now, the final answer is represented in a particular notation like big O of 1. These notations are called asymptotic notations. Let us find more about what these notations mean. Asymptotic notations. Asymptotic notation are mathematical tools to represent the time complexity of algorithm for asymptotic analysis. Algorithm speed isn't measured in seconds, but in the growth of number of operations. The following three asymptotic notations are mostly used to represent the time complexity of an algorithm: big O, theta, and omega. First, we will discuss what omega notation is. Omega notation is a formal way to express the lower bound of an algorithm's running time. That means it measures the best case time complexity or the best amount of time an algorithm can take to complete. Next one is theta notation. Theta notation is a formal way to express both the lower bound and upper bound of an algorithm's running time. That means it measures the average time complexity. Big O notation. Big O notation is a formal way to represent the upper bound of an algorithm's runtime. It measures the worst case time complexity or the longest amount of time an algorithm can take to run. We will learn more about big O notation as when we define an algorithm, we might be more interested in getting to know how slow can an algorithm get. Types of big O notation. Some types of big O notations are constant, linear, quadratic, cubic, exponential, logarithmic, and log linear. Best way to understand big O notation is through some examples in Python code. So let us jump right into some examples. Look at the piece of code shown in the screen. Here, the complexity of the above script is big O of 2, meaning it is a constant complexity. So you might be wondering how we got big O of 2. Well, this is because regardless of input size, the code performs only two steps. That is, adding the constant 10 to the first element in the array and also printing the result. Let's look at another example. Look at the function shown in the screen. The complexity of this function is linear, that is, big O of n. This is because the number of iterations of for loop will be equal to the size of input array. Look at the function shown on the screen. We can see that we have an outer loop that iterates through all the items in the input list. And then a nested inner loop which again iterates through all the items in an input list. The total number of steps performed here is n into n, where n is the number of items in an input array. So, the complexity of this function will be big O of n square. As we have gone through the definitions and examples of the three notations, we will move on to the last topic of this video, that is properties of asymptotic notation. First, we will discuss the general properties. If f of n is big O of g of n, then a into f of n is also big O of g of n, where a is a constant. So to prove this, we will take an example where f of n is equal to 2n square plus 5 and its complexity is big O of n square. So when we multiply a constant 7 to this f of n, that is 7 into 2n square plus 5, we get 14n square plus 35. Here only the constant value changed. The n value didn't change. So our complexity will be big O of n square. Similarly, this property satisfies for both theta and omega notations. Moving on to our next property, that is reflex property. Here, if f of n is given, then f of n is big O of f of n. For example, if f of n is n square, then big O is big O of n square. That is big O of f of n. This property is also satisfied by both theta and omega notation. Moving on to our next property, transitive property. Here, if f of n is big O of g of n and g of n is big O of h of n, then f of n is equal to big O of h of n. In order to prove this, we will see an example. Suppose our f of n is n, g of n is n square and h of n is n cube, then n is big O of n square and n square is big O of n cube, then as per our property suggests, our n value will be also equal to big O of n cube. These properties are also satisfied by both theta and omega notation. Moving on to our next property, symmetric properties. Here, if f of n is theta of g of n, then g of n is theta of f of n. We can see the working of this property with an example. Suppose our f of n is n square and g of n is n square, then f of n is equal to theta of n square and g of n is also equal to theta of n square. Our next property is transpose symmetric property. Here, if f of n is big O of g of n, then g of n is omega of f of n. We can see this with an example. Suppose f of n is n and g of n is n square, then f of n is big O of n square and n square is omega of n. This property is only satisfied for big O and omega notation. Some other properties are as follows. So we have learned what is complexity, types of complexity and also asymptotic notation. Now that we are thorough with our theory portion, let us calculate some time complexity of following algorithms. Example 1. Pause this video here and take a guess on what is the complexity of this problem. Here, the complexity is big O of 2 raised to n. This is because our algorithm growth is doubled with each addition to the input data set. Example number 2. Want to work out this problem? Then pause the video here and try it. You got the answer? If not, it's okay. Let me explain. Here, we have two for loops separately, right? And also, we can see that the for loop runs till the end of the last element in the list. So, the time complexity of one for loop is n. Since we have two separate for loops, we will have our time complexity for this particular function as big O of 2n. When calculating the big O complexity of something, we can eliminate the constant value. So, our time complexity for this problem can be rewritten as big O of n. Let's do a similar problem. Pause the video and work out the complexity of this problem. So let's see. The code in the line tree executes only one time as it only prints the first element of the list. Now, our second code says that it prints the half of our list. So, our for loop loops through the half of the list, making it as n by 2. Our third code prints hello 100 times. So, our time complexity for this solution will be big O of 1 plus n by 2 plus 100. Here, we can eliminate the constant, making it as big O of n. Now you may be thinking, why avoiding the constant isn't a problem while calculating the complexity? Well, in the case of big O, we are looking at what happens as n gets larger. As n gets really big, the adding of these constants or even the n by 2 has less significant effect. We can also drop least significant in our complexity, even if it is not a constant. For example, consider the following problem. If you want to answer the problem, pause the video here. Well, I hope you got the answer. If not, it's okay. Let us work out this problem together. Here, line 2, prints the element in the list till the last element, so making it as n. Now, the next code uses for loop to loop through the same array to get the sum, so it's n square. So, the time complexity for this problem is big O of n plus n square. Here, n is less significant. As n square increases, the value of n plays only a small role. So, we can rewrite the time complexity as big O of n square. Similarly, if time complexity is big O of n cube plus 3n square plus 2000, we can rewrite it as big O of n cube. Let us work out the one last problem to which I'll be discussing the solution here. Pause the video here and work out if you can. This is the algorithm of binary search. It breaks the given set of elements into two halves and then searches a particular element. Further, it keeps dividing these two halves into further halves until each individual element is a set. All such algorithms which work on a principle of recursive division of elements into halves will have big O of log n complexity. So, are you confident that you can now find the time complexity of any algorithm? If then, solve the problem shown in the screen and comment down the answer. That is it for today. Hope you all understood what is algorithm analysis, what is asymptotic notations, and also how to find complexity of algorithms. Any query regarding today's topic, comment down below. Thank you for watching. Please make sure to like, share, and subscribe, and also to press the bell icon to get the notification of my new video. Until then, take care. Bye-bye.